So here we have an activity where we study the refraction of light through convex and concave lenses. So you all are familiar with the lenses. If the refractive surfaces, if the surface of the lens are curved outwards, it is known as the convex lens, or sometimes we call it the biconvex lens. So you can write it as convex lens or biconvex lens. Bi because there are two surfaces and they are curved outwards. If the surface is curved inwards, it's a concave lens, or again we can say biconcave lens. We need a torchlight, that is a light source, a torch. Then we need a comb. Now we need these two to generate a parallel beam of light. Beam of light. So you're familiar with using the torch and the comb. When you place a comb on the table, shine the torch to it, you know the torchlight, there is a circular beam of light. But when it travels through the comb, because of those teeth-like structures on the comb, it forms a parallel beam. So either we can use these two, or else we can use a laser beam, where you have a parallel beam of light. So that is also available in the laboratory. We can use that as well. So these are the materials that we need. A convex lens, concave lens, a torch and a comb. And this is what we are going to do. We will make a parallel beam. So as I said, use the comb and the torch or a parallel beam of laser. Let the parallel beam of light fall on the convex lens and observe the refracted rays. So you will have to place the convex lens there. You need to have the parallel beam of light falling on it like that. The parallel beam of light falling on it like this. So then you observe what happens to this beam. The same way, you have the concave lens. Let the parallel beam of light fall on the concave lens and observe the refracted rays. So here also you will have the parallel beam of light to fall on the concave lens and you observe what happens to that parallel beam. So that is a very simple activity. After that, what you need to do is draw the path of the light in both situations in your notebook. So we will observe what happens when we send a parallel beam of light through a convex lens and a concave lens, and then you have to draw the rays and how they get refracted. So in both instances there will be refraction. Refraction. You have to remember that. Why? Because the lens is either glass or plastic. And here there is air on this side. So when light travels from one medium to another medium, there is refraction of light. So both the biconvex lens and the concave lens, they refract light. So I am sure since it's a very simple activity, you have understood the method clearly. Now let's go to the lab and do the activity. Okay students, so now we are going to observe what happens to a beam of light, a parallel beam of light that passes through a biconvex lens. So here I have a biconvex lens. You can see the two sides or the surfaces are curved outwards. So that is a biconvex lens. So this is what I am going to use now. And here in your activity, you are supposed to use a comb and get a parallel beam from the sunlight. Pass it through the comb so that you get different rays of light. or else you can use a torch and a comb again to get a parallel beam of light. But here I am going to use a laser beam. You can see here it gives a parallel beam of light. So that will be easy for me to demonstrate the activity. So now that we have a parallel beam of light, what I have to do is I have to keep the biconvex lens in between. So the beam passes through the biconvex lens and you can see what happens here. So here students, you all can see initially it is a parallel beam of light. When it passes through the biconvex lens, they all meet at one point and that point is known as the focal point. So here, because the rays all go towards each other, we call it a converging beam. So a parallel beam becomes a converging beam and they converge onto one point, that is the focal point. And the distance between the lens and this focal point will be the focal length. Okay students, so you were able to observe how a parallel beam of light, that is the laser light, was converged by a biconvex lens. And all the light rays converge through one point. And what did we call that? That is the focal point. Okay students, so now we are going to observe how a beam of light, again a parallel beam of light, I told you all in the previous activity also, you can use the sunlight, pass it through a comb so that you see the rays separately. Or we can use a torchlight to obtain a parallel beam of light. Here I am going to use a laser. This also gives a parallel beam of light. You can see the rays parallel to each other. And at the same time, I have this biconcave lens. You can see both the surfaces are curved inwards. A biconcave lens. So what I will do is, I will place it here. Now you can see what happens to the rays. So here you can observe clearly the parallel beam of light coming from the laser light and they are getting diverged. You can see them going away from each other clearly. And as I told you, when you extrapolate, that is when the same rays, when you draw it longer, here you can see between the laser source and the lens, there is a point where all the rays are going through and meeting each other. They intersect each other. That is the focal point of a biconcave lens. Now maybe you will be able to observe it a little more clearly when I move the lens. It is a bit faint, but still you can observe a spot near the laser light where all the beams meet or intersect. So from this you can understand that a biconcave lens diverges a parallel beam of light. Okay students, so you all were able to see what happens to the parallel beam of light when you pass it through a convex lens and a concave lens. What happened when we passed it through a convex lens? It converged onto one point. So there was a brighter spot. All the rays went and met at that point, and that point is known as the focus, and the distance between the lens and that focus is known as the focal point. You were able to observe that. So that was our first observation. So here, if we draw the observation, you were supposed to draw the diagram in your writing book as well. So here, this is by the convex lens. So we need to have the lens here. You can show the convex lens. And then we need to draw parallel beams of light. So they all fall on the lens. So here when we show a parallel beam of light, you know that you have to use an arrowhead to indicate the direction of the light rays. So here all the rays are coming towards the lens. Then what happened? All these rays refracted and they converge through one point. And what was this point known as? It is the focus. The point where all the rays meet on the other side of the convex lens is known as the focus. And the distance between the focus and the lens is known as the focal length. Focal length. So, is this clear to you all, students? You observe what happened, then you draw the diagram to show what happened. So, here also we have to show the direction of the rays. Normally, when we draw a lens, we draw a line like this, that is known as the principal axis. Through that also light rays can travel, they travel straight, and all the other rays converge onto one point. So, here light rays converge. Light rays converge onto the focus. After that, what did we do? We used the biconcave lens. There also we send the parallel beam of light, and there what did you see? The rays get diverged. They go away from the lens. So that is the next observation. We had the concave lens. Concave lens. Again we had the we need to draw the principal axis. Then we need to draw the lens. And we need to have the parallel beam of light. So what happened here? They diverge. They go away like this. All the rays are diverging. They are going away from each other. So that means, unlike in the previous one, they will not meet on the other side of the lens. So what we do is, we extrapolate these rays to the same side from where you got the rays. Now here, the rays come from this side. This is the incident beam of light. So what we do is, we extrapolate it like this. If we extrapolate it, you can see that they all look as if they are coming from one point. So that point is known as the focus. So this is the focus, and the length or distance between the focus and the lens is the focal point. So do you all understand this now? And students, remember, here the lines are not exactly straight, but when you all draw the ray diagram, you will use a ruler So you can draw proper straight lines even when you extrapolate. When these are exactly parallel, then you will be able to see that all the rays will look as if they are coming from the same point. So that is the focus of the concave lens. So here what happens is, here the beam, the light is diverged. So a convex lens converges the parallel beam of light. You have seen that here. It converges the parallel beam of light, whereas the concave lens, it diverges the parallel beam of light. So is this clear to you all, students? And that was the activity. And what is the lens that is present inside our eye? It is a convex lens. So that lens also converges the parallel beam of light over the beam of light. The light rays are converged onto the retina, and then the image will be formed. So we are trying to understand how the lens inside our eye forms the image. So with that, I will move on to the next slide. A convex lens. So when we pass a parallel beam through a convex lens, a parallel beam of light refracts through the lens and gets converged. So that I explained to you all. The point that collects the light rays in front of a convex lens is called the focal point. You were able to observe that. And the distance between the lens and the focus or the focal point, it's the same thing, focus and focal point, is known as the focal length. The same way, if we take a concave lens, a parallel beam of light refracts through the lens and gets diverged there. Here the rays after refraction appear to come from a point called focus. So this is how light is refracted by convex lens and concave lens. So if we look at an object through a convex lens, it has to form an image. So normally you all know, now if we have the, let's say there is an object like this, let's say this is an object. So here you have the convex lens and you know the image forms on the other side of the lens, and you all know it is going to be an inverted image and it's going to be a small image. So considering this is the lens of the eye. So here is the object and this will be the image. You all know it's going to be an inverted image, but it will be interpreted as the upright image. But now if we consider the distance or the length between the object and the lens. Now this is the object distance. And this is the image distance. So based on the object distance, the image distance will change. Usually when the object is close to the lens, image will be away. And when the object moves away from the lens, the image will come closer to the lens. So it's like an inverse relationship. When the object is far away, image is close. When the object is close, image is far away. That's how an image is formed by a convex lens. To understand this, we will look at an activity. Activity: study how an image of a close object forms far from the convex lens, while far object forms an image close to the lens. So, the two different types of images formed by the two different objects at different positions. So to understand that, we need a convex lens. Then we need a candle that will act as the close object. Then we need a matchbox again to light the candle. We need a lens holder. And we need a screen. We need a screen. Now you all can also make this screen. Say you can take a white sheet of paper, paste it onto a cardboard and use it as a screen, or there are screens available in the laboratory. We can use one of those. So a convex lens, a candle, matchbox, lens holder and the screen. Now this is what we are going to do. The method. We have to fix the convex lens to the lens holder. Using the lens, get a clear image of a distant object. So the first thing is, let's say a faraway object, maybe a tree that is outside the window of the laboratory. We have to get the image. You have the convex lens there and you need to get it on the screen. Get it on the screen. You have to get a clear image. Then after that, what we do is, we have the same lens, but now we have the candle. And then we try to get the image. So here you will see that the image forms on the screen there. So you can see a far object, the image distance is less. A close object, the image distance is far. That is what you have to observe. So fix the convex lens to the lens holder. Using the lens, get a clear image of a distant object on the screen. Light the candle in front of the lens and get a clear image on the screen. Always it has to be a clear image. Measure the distance between the lens and the image. That is the image distance in both cases and compare. So here this is one distance, we'll say D1, and this is the second distance D2. So this is when the object is far, this is when the object is close. So then you have to compare the two distances. Now that you have understood the activity clearly, we will go to the lab and do this activity in the lab. Okay students, so now we are going to observe how an image is formed by a biconvex lens. So here you can see both sides are curved outwards. You are familiar with the biconvex lens. And here I have a stand. I will fix it to the stand. And although the stand is here, to identify the position of the lens, we have a mark there. So when I am moving it around and also to measure the distance, it will be easy for us. Then we have a screen. This is the screen that I am going to use and a measuring ruler so that we can measure the distance between the lens and the image once it forms on the screen. So first I am going to focus or get the image of an object that is far away, something that is outside the window. So to do that, first I will place the ruler, then I can adjust the lens so that you will be able to, now you are getting an image. I will make it to 0 position. You are getting an image, but it's not very clear yet. So we have to make it clear so that we can see it properly. I have to adjust the lens so that you get it clearly. So now here you can see the image of a plant. So that is a faraway object, a distant object. And if we take the proper measurement, you can see here it's very sharp image. So at that point, if you look at the reading or the measurement, the length between the lens and the screen, it's 9 centimeters. So this is an object that is far away from us. And we have got the image on the screen, and the distance between the image and the lens is 9 centimeters. After that, I will need another object, that is the candle. So I have to use a lighted candle. So now I am going to use a close by object. For that I am going to use the candle flame, a lighted candle. So here if I have it at that same position, 9 centimeters, you can only see the far away image. You can't see the image of the candle. So here the candle is a little taller. So what I will do is I will lift the lens as well. So now with that, if I move the lens a little bit more, so I am going to move the candle a little bit more so that we get a more better image. You can see a little bit more clear image now. So still the object is closer to us, closer than the previous object, but you can see the distance between the screen and the lens. Now it is 19 centimeters. So earlier when the object was far away, the image distance was 9.5 centimeters. Now when the object is closer to the lens, the image distance is 19 centimeters. So when the object is far, image distance is short. When the object is close, the image distance increases. So that is what we can observe from this activity. Okay students, so you were able to observe what happened in the lab. When we try to focus the image of an object that was outside a tree, you were able to see that the image distance was less. And when we use the candle as the object, the image distance was more. So now you all can understand what happens there. So if I write down the observations, image distance was less for far object and image distance was more for close objects. So from that, what can we conclude? What is the conclusion? The image distance depends on the object distance. So image distance depends on the object distance. And to make it more specific, we can say when object comes closer to the lens, the image distance increases. Or you can say when the object distance decreases, image distance increases. Or when the object distance decreases, image distance decreases. So that can be concluded from the activity. So image distance was less for far object. It has to be image distance was less for far object and the image distance was more for close objects. That was our observation, and the conclusion was that the image distance depends on the object distance. That means when the object comes closer, the image moves far away. So now with that, I will move on to the next slide where we again look at those conclusions. So you can confirm that the image distance is more when the object is located close by than it is located far away. But in the eye, the distance from the lens to the retina cannot be changed. That you all know. So here we have the eyeball like this. This is the lens and that is the retina. So this distance cannot be changed. This is fixed. So from the activity, you all have understood that the image distance changes. But here the image distance is fixed. So then how do we see objects close to us and far away? That you all know because you read the book, you have the book close to you. That's a close by object. Then at a different distance. Then again we look at the stars, the moon, the sky and all that. Those are very far away objects. We see them clearly as well. So that means there has to be a way that the image forms inside our eye for both the close objects as well as far objects. To understand that, how can we clearly see the objects close by and far away? So this happens because the lens of the eye has the ability to increase or decrease its curvature to the required size. So that is very, very important. I mentioned this to you all before also. The lens in our eye can change its curvature. And what is the structure there? You can remember this is the eye lens. Now this is connected with the ciliary muscle. This is the lens and this is the ciliary muscle. The ciliary muscle helps to change the curvature. When the ciliary muscle contracts, this becomes thin. The curvature decreases. Ciliary muscle relax and the curvature increases. So by that way, the curvature of the lens can be changed. Thereby, you can see close objects as well as far away objects. To understand that, we will look at an activity. So, activity, study about the image formation of a distant object and nearby object without changing the image distance. So, previously students, you all can remember we looked at the activity where we changed the distance. So, you all know for a far away object, the image forms closer. For a close by object, the image forms far away from the lens. But in the eye, we cannot change the distance between the retina and the lens. That is, the image distance cannot be changed. So then, how can we observe the different objects? Objects that are close by and objects that are far away. So, we are going to do this activity to understand that concept. So, to do that, we need two convex lenses. So, both these are convex lenses. I will write it commonly here. Convex lens with high curvature. That is this one. You can see here, it's a more broader lens. So, convex lens with high curvature. And what about this one? It is with less curvature. So, and less curvature. So, we need two convex lenses or biconvex lens. One with less curvature, the other one with high curvature. Then as an object, we need a candle. To light the candle, we need a matchbox, a lens holder, and to get the image, you all know we need a screen. So here we need a screen. So the materials are, we need two different types of biconvex lenses, one with less curvature, the other one with more curvature. We need an object, that is the candle, and a lens holder to place the lens, and we need the screen to get the image. So now we will see how we are going to do the activity. So this is the method. What we will do is, we will have the lens at one point and we will fix the screen here. So this is the screen and that is the lens. So the distance between the screen and the lens is going to be the image distance. That is not going to change. So we'll see what we have to do. Fix the convex lens with less curvature to the lens holder and get a clear image of a distant object on the screen. So initially with less curvature, we are going to get the image of a distant object. So first you have the less curvature convex lens here and a distant object, maybe an object outside the lab, outside the window. So that's a faraway object. Then we get the image on the screen. We try to get the clear image. Then what we do is, without changing that distance. Initially to get the first image, we might need to adjust the lens. But without changing the distance, we do the second step. Fix the convex lens with a higher curvature to the lens holder without changing the distance between the lens and the screen. That's very important. Without changing the distance between the lens and the screen. That is what I told you all here. The image distance is going to be fixed. Now get a clear image of the lit candle onto the screen. So first we have an object that is far away. Then we get the image. Then we have the close by object, that is the candle. With that also we get the image. But initially we use the lens with less curvature for the far away object and lens with high curvature here, that is for the close by object. Then you look at the image formation. Is that clear to you all, students? I will repeat the procedure again. We have to fix the image distance. Like in our eye, we are not going to change that. And we are going to use lens with different curvatures to observe objects at different distances. Is that clear to you all? So then we will do this activity in the lab. Okay, students. So you all know we need to observe close objects and far objects. And to observe that, we need to have convex lenses with different curvatures. That is what we are going to observe now. So here I have two convex lenses, one with less curvature and the other one with high curvature. So now what I am going to do is, first I'll use the lens with less curvature. I will place it on the lens holder and try to focus an object that is far away. Now can you all see the image of a leaf there, a part of a tree? You can see the image of the leaf. That is a clear image. When I position it somewhere here, you can see the images. At this point, you all can see a clear image of the leaf. So a far object with a thin lens, that is a lens with less curvature, we can get a clear image. So now at the same time, you all can see there is no clear image of the candle on the screen. Now I am going to change the lens. Now I am using a lens with higher curvature. Now here, students, you can see the candle is a close object and you can see the image of the candle clearly. But you can't see the image of the far object clearly. So from this observation, you all can understand to observe a far object, we need to have a lens with less curvature. Whereas to observe an object that is close, a close object, we need to have a lens with high curvature. So inside our eye, the distance between the retina, that is the screen, and the lens cannot be changed. So the image distance is fixed. But when the object distance changes, the lens of the eye changes its curvature to observe that object. That is what we can understand from this activity. Okay, students. So you all saw all the observations. You were able to observe them clearly. What happened first? We looked at an object that was far away from the lens. So that is the first observation shown to you all here. When we use parallel rays, that means the object is far away. So here, far away object. To look at the far away object clearly, what type of lens did we use? We use the lens with less curvature. So here, this is with less curvature. And you were able to get the image there. So here, this was the image distance. Let's say I will mark it as D. Then in the second step, did we change the image distance? No. So that was also kept as D. But what we did was we changed this lens. This was with high curvature. And the object is close object. So we were able to get a clear image of a faraway object using a lens with less curvature. And then we were able to get a clear image of a close object using a lens with high curvature. So that is what happens inside our eye also. So before I explain that, what I will do is I will write down the conclusion. So from this, we can have a conclusion. What can we conclude? When the image distance is fixed, or you cannot say image distance cannot be changed. Either way, it's okay. Cannot be changed. What happens? To observe far objects, you need convex lens with less curvature. And to observe close objects, you need convex lens with high curvature. So that was the observation. So from that, what can we conclude? We need to change the curvature of lens depending on the distance of the object. So here we can say the curvature of the lens has to be changed according to the object distance when the image distance is fixed. So that is what we observed before also. In the activity, you all can understand, students, when we want to look at an object that is close by, we need to have a lens with high curvature. If we want to look at an object that is far away, we need to have a lens with less curvature. So the lens in our eye has the ability to change its curvature. Do you all understand that clearly? I am sure you do. With that, I will move on to the next slide. The focal length is comparatively high in low convex lenses. We will look at that. So here, if we have a convex lens with low curvature, a very thin lens. So this is low curvature. Then the focal length is high. This is the focal length that you all know. Focal length high. So when the curvature is low, focal length is high. What type of objects can be observed clearly here? The far away objects. So here we can observe the far objects clearly. Far objects. That is the first point. The focal length is comparatively high in low convex lenses. Lens with less curvature. Is that clear to you all? So then, the second type, where we have a lens with high curvature. Now, compared to this, you can see that lens has a high curvature. Then the focal point, what I mark as F, is the focal point. And here, low focal length. When the curvature is high, focal length is less. So the focal length is relatively low in higher convex lenses. That is the second diagram. Lenses with a higher curvature. What do we use that to observe? We can observe close objects clearly. So you all can remember, from close objects the rays come like this, like divergent rays. Whereas parallel rays come from far away objects, and rays that are divergent, they come from close objects. So this is what our eye does. When we need to look at an object that is closer to us, let's say you are reading a book, the lens inside our eye becomes broader. The curvature increases. When you want to look at an object that is far away, then the lens becomes thinner or the curvature decreases. So that's how our eye is able to look at objects that are close by and far away, by changing the curvature of the lens. With that, I will move on to the next one. So here we have an assignment. Make a water lens using necessary items. So here you need to make a water lens. Now you all know normally the lens that we use in the lab as well as the lens that are used for spectacles, usually they are made up of glass, or nowadays it's mostly made up of plastic. Now glass and plastic, they basically have the same function, but the advantage is plastic doesn't break easily. You all know, especially for spectacles, when we use glass lens, if we drop it, then there is a chance that the lens can break very quickly. But that doesn't happen very easily with plastic lenses. So those are the materials used to make lens. But at the same time, we can make a lens using water. So here the assignment is to make a water lens using necessary items. By increasing or decreasing the curvature of the lens, get clear images of a lit candle placed in different places without changing the image distance. So what we did as the activity before, they want you all to try it at home, but with what? With water lens. So how can you make a water lens? There are different ways. You all are very innovative, so you can think of many different ways. I will tell you all one method. You can try that as well. Now you all can get sealable plastic bags. Very transparent, normally the transparent plastic bags that can be sealed. So you can get bags of the same size. Let's say if they are square, it would be ideal. Then what you can do is you can cut. Now you have plastic bags. Bag, and it has to be transparent. Transparent. And what you do is you cut 2 pieces of cardboard. That also almost the same size or slightly larger than these plastic bags. Then what we do is we need to have 2 cardboards of the same size. They have to be square is better, and in the middle you make 2 holes of the same size and they have to be circled. Then what do? You fill water into the plastic bag. You can seal it. You don't fill it completely full, but there can be a certain amount of water. You close the plastic bag so that the water doesn't leak out. Then what you do is you keep the plastic bag in between the 2 pieces of cardboard and press them together. Make sure that all the water is contained within this area. So what do? You have the cardboard here, then you have the bag containing water, and again on top you have the board. So this is the board, then bag with water, and again the board. When you press it together and make the water to come into this circle, you can see it will rise up like a lens. And then what we can do is we have the board like this. We can put bulldog clips. These are the bulldog clips or the paper clips. If you staple it, then of course there is a possibility that the water can leak. But if you put a bulldog clip, then it will hold the cardboard and the bag containing water in place. And also it's easy to remove, and you can either pour more water or you can reduce the water. Like that, you can change the curvature of the lens. That is the water lens. So did you all understand what you are supposed to do? Take 2 cardboards, make the same size circular holes in it, and have a plastic transparent bag with water. Place that bag with water in between the 2 cardboards like this, and when you press them together, you can see the water rising on either side like a lens. And then you put bulldog clips to keep it in place. Then you try to observe the objects. So what are you supposed to observe? You need to have a candle. So this is the first step where you have made the lens. So here you will have the lens in the middle here also. You will have the lens in the middle. So that is the water lens. So this is going to be the water lens. Then what you will do is you will have the candle here and hold the lens somewhere close. So this is a close object. And behind you need to have a screen. and observe. The same way, what you can do is you can change the object. You can take the candle away from the lens. Then accordingly, you will have to adjust the screen in order to get the clear image. So there also, what will you see? When the candle goes far away, the image will come closer. Or when you bring the candle closer, image will be far away. So close objects, image distance is high. Far objects, image distance is less. The same thing you can repeat with lens with different curvature. How can you do that? You can change the amount of water that is present inside the bag. When you have less water, the curvature will be less. When you have more water, the curvature will be more. You can make a lens with higher curvature, again repeat the activity and observe how the image forms. After that, if we go back to the activity, you can see here by increasing or decreasing the curvature of the lens, get clear images of a lit candle placed in different places without changing the image distance. So first, I explained to you all where we change the image distance. Here we change the image distance. But when you fix the image distance, then you will see to observe the far object, you need a lens with less curvature. And to observe the close objects, you will need a lens with high curvature. That is how you will observe these objects or the candle kept at different places. So, if I write that like a summary for you all, you will have close object. Then you need to have a lens with high curvature. And for far object, you need to have lens with less curvature. So again, the same observation like what we got for the activity in the lab. So is it clear to you all now? I am sure it is. So then, now we will see how images are formed inside our eye. You all are familiar with the structure of the eye. You know the cornea, the layer that is transparent, allows the light to pass through and it goes through the pupil of the eye, and the size of the pupil is controlled by the iris. When there is more light, the iris becomes relaxed, so the pupil decreases, size of the pupil decreases. When there is not enough light, by the contraction of the iris, the pupil dilates, it becomes larger. So, more light can enter your eye. Then they pass through the aqueous humor and fall on the lens, that is a biconvex lens, and biconvex lens make the image form on the retina. And from the retina, on the fovea or the yellow spot, a very sharp image forms. And what are the cells that are responsible for the formation of images? Cone cells and rod cells. And the information of the image is taken to the brain by the optic nerve. So, all that is familiar to you. Now, we will see how images are formed. So, we'll draw a ray diagram for an image formed of far object on the retina of the eye. So, you all know the structure of the eye. Now, if we take it as a spherical shaped structure, it's almost spherical, but you all know there is the optic nerve going from here and all that. But we will just focus on the eye lens and the retina only. Inside that, students, you all know the presence of biconvex lens. And here between the lens and the retina is the image distance, and that doesn't change. So then, if we try to draw the ray diagram for an image for a far object, now this is going to be a far object, the rays are going to be parallel. Always from a far away objects, the light rays that come to our eye are going to be parallel rays. So the rays that reach from far object can be considered as parallel rays. So if we draw parallel rays here, if I draw this as the primary axis, then we have parallel rays coming towards the eye. And to denote the rays, we need to use arrows, arrowhead to show the direction of the light rays, and they will all converge onto the retina. So here you can see the light rays converge onto the retina. And what type of an image is formed? So here the image will be inverted image, inverted. So the image will be an inverted image. And when the optic nerve carries the information regarding the image to the brain, there it will be understood as an upright object. That you all know. So this is how an image forms for a far object. The rays that reach the eye from far object get refracted. This is an important term, through the lens and converge onto the retina, making the image on it. So you all have to remember all these terms. This is how image is formed by a far object. Then let's see how an image is formed by a close object. Ray diagram for an image formed of close object on the retina of the eye. So again, we need to have the eyeball. So that is going to be the spherical shaped eyeball, and you will need to draw the lens there. Here students, you don't have to really show the difference in curvature. If you indicate the presence of the lens, that's more than enough. So then we will draw the ray diagram. For that, you need to have one ray that is going along the principal axis, the center axis. The ray that is traveling through the principal axis does not get refracted. It travels directly. Then, now the rays that reach from close objects, now we are looking at an image of a close object, and that is going to be diverge rays. I told you all that before also. From a close objects, we get diverge rays. You know what diverge rays are. They start from one point and they go away from each other. So we will get diverge rays. All those rays will come and fall on the lens, and they get refracted again onto the retina. So that is the point where the image forms. These are the diverge rays and these are the refracted rays. So here again an inverted image will form on the retina. In both cases, the image distance does not change. The rays that reach the eye from close object get refracted through the lens and converge onto the retina, making an image on it. So this is the ray diagram for the image formed for close objects on the retina of the eye. So in both these instances, we looked at the ray diagram. Previously, we looked at the ray diagram that for a far object. Now, this is a ray diagram for a close object. In both instances, whatever the object distance is, always the image distance is fixed. Image distance is fixed. y, the distance between the lens of the eye and the retina cannot change. So that is fixed. And the image that forms on the retina, what are the properties or characteristics of the image? I told you all it is an inverted image. Always an inverted image forms, but when the information goes to the brain interprets it as the correct image. And also we call it a real image. The reason is it forms on the screen or it forms on the retina. You all are familiar with that. The image that forms on a screen is known as a real image. So here, because it forms on the retina, we call it a real image. And mostly, when you look at things around you, say you look at a tree, the tree is a very large object. But the image that forms inside the eye has to be a very, very small image because you know the size of your eye and the tree. So usually it is an image that is smaller than the object. So the next one is image is smaller than the object. Image is smaller than the object. So these are the things that you have to remember, students. The image distance is fixed. It is an inverted image. It's a real image because it forms on the retina, and the image is usually smaller than the object. So that is common irrespective of the distance of the object. It can be a far object or it can be a close object. So with that, I have completed the discussion on the structure of the eye and how images form inside the eye. So after this, we will be discussing the disorders of eye or eye disorders.